well, good morning, everybody. Thanks for joining today. My name is Darren McGuire. I come to you from Siemens Energy. And today, very excited to talk to you about ways that you can use artificial intelligence to enhance energy management for power plants. So this means to achieve good outcomes and things like overall plant efficiency, right, bringing down costs for power generation, and also to better capitalize on the sale of electricity or electricity services. These are the topics that I want to go over in the presentation, right? So first, I think it's good that we align on some terminology. I'll explain what do I mean by energy management. Energy management can mean a lot of different, it's a broad term, right? And you maybe have already heard of it before. And so it has a lot of different meanings depending on your perspective of the energy industry. So to make this presentation more effective, I'll give you my definition for it, right? And that'll frame the whole conversation. After that, we'll take a look at some of the trends in the energy industry. And the reason why we do that is because I think these trends have an impact on our power plants and how they address these impacts and it creates the need for an energy management solution. And then after that, we'll deep dive into what is an energy management solution. Right? We'll go through the key building blocks and the elements of an energy management solution, and then we'll wrap it up by talking about a couple of use cases so we can connect the dots between the concepts we talk about, and then you can see how it applies in actuality. Okay, so first up with the definitions of energy management. Move forward one more. So I would tell you that energy management is using software capability to create simulations, forecasts, and optimization for the purpose of creating a plan that leads you to better business outcomes. Okay? Business outcomes is also like a pretty general term, means a lot of different things to different people. In particular, the energy industry, we have power plants that generate the electricity. We have the power grid, right, that needs to move the electricity, distribute it around. And then we have consumers of electricity. And all of these areas, I think they may use the term energy management and want to achieve better business outcomes. But for this conversation, I'm going to focus on the power plants, the ones that generate the electricity, right? So we want to think about the business outcomes that they want to achieve. They want to do things like bring down the cost per unit of megawatt generated. They want to be able to better sell their electricity, to capitalize on opportunities to sell that and to sell services around the electricity or maybe steam production. So these are the types of business outcomes that we want to use energy management to have an impact, and we'll focus on power plants specifically. Okay. So now we'll jump right into some of the major trends throughout the industry. I think a good theme for maybe this whole presentation is the word complexity, right? I would make the argument that we see an overall increase in complexity within the energy industry, certainly for power plants as well, meaning there's an increase in the complexity of the type of assets that we use to produce electricity, the way we use them in combinations, microgrids, grid services, right? All of these things are always evolving, new technologies being infused, and this makes it a more complex process to really plan how are we going to use our electricity. These trends here might look familiar to you. I would make the argument that these are all kind of still in place today, right? Where over the last 10 years, there's definitely been a shift to more renewable generation that brings with it a level of intermittency to its electricity production, so that needs to be considered. There's been a general trend of decarbonization, right? Trying to move away from high carbon producing forms of electricity. Demand side management, right? So this is now services that the power grid may offer to consumers of electricity to actually pay them, right, to to reduce the amount of consumption at certain times of the day. Decentralization is a major theme, right? So there's been kind of a shift from these very large energy generating centers to smaller, more geographically dispersed generating centers, right, that now need to be considered. How would you coordinate the operation of those and run them in a remote type of way? TSO regulations, right? So the transmission system operators have heavily focused on trying to keep everything in balance and offering services that incentivize power plants to help them do that. Digitalization, right? There's more and more things now connected. We're producing more data. We have more sensors. We're trying to use that data to make better decisions more quickly. And lastly, a focus on energy security, right? We want to make sure that there's always enough energy available to meet the demand needs and make sure that that is stable, secure from cyber threats and also from physical threats. These trends, I would argue, is having an impact on the power plants themselves. And these are the impact, the way it's being impacted, right? It has led to an increase in market volatility, right? So demand for electricity, price that's paid for that electricity, how that changes over time. Power plants need to consider offering their electricity in shorter and shorter market intervals. Everybody is usually interested in maximizing the efficiency of the assets that you have available. And as we talked about, these different types of assets now being used in combination, that it's a more complex effort to manage all of this equipment. And so what this, I think, is telling us, right, is that the process of trying to plan how do you want to produce your energy to meet your goals is getting more and more complex. It's more and more difficult. And so this is where our energy management solutions come in, where we need things that are going to help us be able to create these plans in a more effective way. When you look across the landscape of what equipment, what solutions do we use today to operate power plants, right, is a combination of things. So of course, every power plant is going to have something like a SCADA system, right, that's going to give you transparency into how the equipment's performing. You can do some supervisory control, switch modes, turn things on and off, handle alarming. You have the primary asset controllers, right, that are going to receive commands like make this gas turbine produce 100 megawatts, and then it will manage the subsystems. How much fuel do I need? How much air intake? What temperatures do I set to, right, to achieve that output? And possibly if you have multiple types of generating assets, you need a thing like a hybrid controller that's going to synchronize the electricity that's being generated from these different assets into a single input to the grid that's synchronized to the grid frequency and can monitor that grid frequency, and as it needs to change, it can then coordinate the response from the plant so that the power plant is always producing electricity that is in synchronization with the grid for frequency and voltage. All of those elements are involved in the execution of producing electricity. The element that we want to layer on top of it is the plan, right? Before you can tell the controller that we want the gas turbine to produce 100 megawatts, you need to make a plan for like, well, why do you need that? At what time? For how long? And this is where we see real benefits of using artificial intelligence techniques to help you create systems that will simulate the operation of your power plant through many, many scenarios very rapidly, will help you create a forecast so you know what your target is going to be in the near future, is what you have to produce, and to create an optimization engine that is governed by the business rules of your power plant to bring these things together, to bring the simulations with the forecasting together, to produce a plan that you can follow for, you know, a given time horizon, say 24 or 48 hours. This is where we really see benefits in using artificial intelligence type capability. So we would call that an energy management solution, right? When you have a system that can do the simulations and the forecasting, the optimization. And the way we start off kind of building a system for this is to focus on the optimization, to provide the governance around what type of business rules, what are the objectives that we want this system to try and create a plan for, right? So we ask it things like, I've made commitments to deliver electricity in the near future, so what are my demand obligations? Do I have any power in reserve? Should I hold some in reserve? What can I do with that reserve? Is it possible that I could sell that into different type of markets? What is the best combination of generating assets to fulfill that commitment? Which of my plants is most efficient that I want to put priority on? You develop really the fundamental business questions that you're trying to satisfy into the optimization governance. And then around that, we want to add the elements of forecasting, right? So we know or have a good idea of like, what is it that we need to offer? How much electricity are we going to produce? We want to do things like have weather forecasts, right? Because weather impacts the output of all different types of generating assets. Look at things like fuel prices. What are electricity prices going to be? What are they going to be in the different markets that might be available, right? This would tell us when and how much electricity maybe we want to bid, or what assets we use at any given time. Is the demand forecast. So there's a forecasting element that sets your objectives. Then you also need to have a model of your energy system, right? Something that allows you to predict your future capacity and to simulate many, many different kinds of operating scenarios so you can find the most efficient way to use your assets to fulfill the demand that you just forecasted. And there's another element here that ties in with the execution that we talked about earlier, right? I said all of this is for the purpose of making a plan. Once you have that plan, you want to feed that plan to the asset controllers, right? So that they then know how to operate the plant. And of course, the plant will try to follow those plans, but at any given time, the transmission system operator may request a change to keep the grid in balance. Who knows what happens, right? Maybe equipment doesn't perform the way it was expected. So you need a feedback loop. You always need to be state aware of the assets so that you can continue to plan for the upcoming future operation. In this cycle, these are the real elements of building an energy management solution, and it just continuously runs on this cycle. Let me deep dive into these elements a little bit further, right? So I said you need a model of your energy system so that you can run simulations and forecast capacity, right? This is kind of a visual representation of what an energy system model might look like from us. So what we do is we have a library of component models. We want to be able to model every single controllable asset at the power plant. You want to establish connections between these assets because the output from one could be the input for another, right? So a simple example would be the heat output from a gas turbine is going to go into your HRSG, right, for creating steam. So there's a relationship between all of these different assets, and you want to establish that connection. Once you have that base model in place, now this is where you want to start using machine learning techniques to further refine the model and get this model to perform very closely to the plant that is in focus, right, under all kinds of scenarios. So we need to go back and we need to gather a lot of historical operating data. I would say at least a year's worth of historical operating data so that intrinsic within that data, you will be able to see how the plant performs differently under different weather conditions, under different operating modes. And the techniques that are used here now build that information, will capture it into the model, and that's very useful going forward for doing simulations and that we talked about, right? So here we want to use like supervised learning techniques or maybe time series or regressions to help train these models to match the power plant in focus. And I'll add to it, because I know maybe that makes it sound like it's a simple process. This is not a trivial process, I don't think, at all. There's always an element of looking at historical data that tells you how the equipment did operate and maybe how it's changing over time. But what that doesn't tell you is how the equipment could operate, right? And so this is also an important element if you want to create a really accurate, useful model, is understanding or working with the customers that we do to really open up kind of the possibilities of how this equipment could be used and to put those types of constraints into the model to see if there's different ways of running the plant that could be used. But once we do this, now we have a system for the simulations. Simulation, that's great, but you also now need the forecasting element that we talked about, right? You need to know, like, well, what is it that I'm trying to achieve with the simulation? Am I trying to achieve 100 megawatts for the plant, 200 megawatts? This is where you need some kind of forecasting element. And we can create forecast models here as well using similar techniques. You don't have component models, but you would go and collect a lot of historical information, split this up into training and test sets, and you create things like a weather forecast or a forecast of the electricity pricing for the market. Those things may be obvious to you that, well, they probably already exist, right? And so that is a possibility. You don't necessarily have to create new forecast models here. You can just use existing forecast models, maybe that are already in use or just well-known, and feed them into your energy management solution. And now you've at least created the forecasting element that you need to work with your simulations. The third element and final piece here is now in the optimization. So the optimization is really where we're going to bring together the forecasting and the simulation tool to generate the plan for operating, all governed by what are the key business constraints and physical constraints of the equipment that you can simulate it into, right? So here we would use techniques like mixed integer linear programming to give us very precise and constraint-aware solutions. What it does is it may take a time horizon that you want to create your plan for, say 24 hours, and split it up into very small time increments, and then solve the optimization for each of those time increments sequentially. So they build on top of one another, right? This is a very good technique for optimizing, and it allows you to create your plan, right? And then you need to send that plan to the asset controllers like we talked about, right? To go and follow it. But what happens here is that 5-10 minutes later, new information becomes available, right? Like I said, maybe the transmission system operator called the power plant and said, hey, we need an extra megawatt to balance the grid. You have to kind of change what's going on. Maybe some of the equipment didn't perform the way it wanted to. The weather didn't turn out the way you wanted to. You need to be able to consider that new information. So here, this is what we call the rolling time horizon, where after a certain time increment, and this new information is received, we restart that whole process again of forecast simulations in the optimization engine to formulate a new 24-hour plan. And in that 24-hour plan, like I said, split up into little tiny time increments that's telling the equipment, be at this set point at this time, change at another time. So we now have recreated that plan and again send it to the asset controller, right? So 5 minutes ago, I just sent you a plan of how to operate for 24 hours, and now I'm sending you a new plan of how to operate for the next 24 hours, right? And this is called the rolling time horizon. This is a way that we can keep the power plant in a continuous state of optimization, right? Always using the latest information to account for things that can't be forecast or unforeseen circumstances, using this rolling time horizon type technique. Okay, so those are really the key elements behind an energy management solution, right? The simulation, the forecasting, and the optimization. Let's tie this in now with a couple of use cases so that you can see how it applies in real life. So the first use case I'll talk about here, this is a district heating facility, okay? So what that means is this power plant is responsible for producing steam that goes into a heating network that the local city uses for heating purposes, right? And this is the primary obligation for the power plant. They have to be able to fulfill that need. But they also have electricity generating equipment, and they can sell that electricity to the power grid as another revenue stream. I talked about complexity as a theme. So I would describe this plant as very complex in terms of the number of assets that they have, the different types of assets. So they have some assets that generate electricity and steam. They have some that generate steam. They have some that combine heat and power. And also, so that's complex, but then also the delivery that they have to fulfill are quite complex, right? They have this heating demand that they have to be able to forecast, and they always have to be able to fulfill. But then they also want to be able to run their electricity generating equipment to sell electricity, but that equipment also produces heat and steam. And so they're constantly having to make decisions around which assets do we start up so we can fill the heating demand, and then layer on top of it which assets do you use at what time to be able to maximize your sale of electricity. So this is always also a complex plan that has to be put in place. And so we came to this customer, we worked through the process of building them an energy management solution, and this is what they use today, every day, to create the plan for how they want to operate their plan. And we think they've gotten very good results out of this. Let's take a look. So these are again, going back to the elements that we talked about for the energy management solution, this is a look at what the energy system would look like, right? Pretty complicated set of connectivity and components that help us simulate all different kind of combinations of how that equipment can be run. Now we need the forecasting piece to it, right? So here we created a day-ahead pricing forecast for the customer. So what you're just seeing here, a visual representation of that. We give the red line representing like the current time, and then you give a forecast with an uncertainty band around that forecast, right? So you have some indication of volatility. And then you can go back in time and take a look and see how well the forecast aligned to the actual settled prices, right? This price forecast obviously being very important because this is going to tell us the times when this plant should ramp up the most of their electricity to be able to offer to the market. And that's nice, but they also still have this obligation of fulfilling the district heating requirements, so they also have to be able to forecast the district heating demand throughout the day so they can plan appropriately. And there's another element here is the availability of the assets at the plant. Anybody familiar with power plants, we know that there's obviously maintenance that has to happen. Things don't always work the way they're supposed to, so we need to be able to get that input into the system so that the model of the energy system knows which components to take out of consideration or partially use, depending on what kind of availability they are. So this is also an important input into the forecasting or the planning piece. Okay, now this is the plan, right? So we put that into the optimization, and out comes the plan. What you're looking at here is another visual representation of, I forget how long this is, 48 hours, 72 hours, for how each of the assets at the plant should be dispatched, how many megawatts should they be producing, and at what time. So the different colors in the top chart are representing the different assets. So you can see that there are some that are just kind of your base operation, your most efficient equipment. And then as the colors change, there's certain assets that we fire up at certain times when we believe that the pricing is going to be most favorable, right? And this is all done in advance, so we're trying to forecast when are those prices going to be good so that we can make this dispatch plan and this commitment to the grid. And obviously the goal here is that you maximize the electricity production at a time that's consistent with higher prices, and then bring that production down at a time when maybe prices are not so favorable, right? It's a simplified description of kind of what's going on, but That's the process of making the plan, and then within all of that, this is related to electricity sales, again, is still the district heating requirement that has to be fulfilled the entire time. Okay, I jumped ahead really kind of quickly there, but so that's a use case, very complicated, I think, plant and using fossil burning type assets to meet several different deliveries of steam and electricity. This here is a second use case now where we're going to just talk about renewable equipment, right? So in this use case, you have a wind park and a battery storage system. And so the customer wants to use that battery storage system to be able to offer ancillary services to the power grid. The challenge is that they have one pipeline out to the grid. When the wind farm is producing at max capability, it will consume all of the capacity in that line, right? So you can't use the battery during that time, except if you're overproducing, you'll be able to dump some of that power into the battery. And so here we need the energy management solution to be looking at the forecast of wind generation, understanding how much of the line capacity that's going to take up, and when there is availability in that line capacity, making sure that the battery is ready and available, telling an energy marketer that, okay, now this battery is going to have this much capacity available for this much time that you can offer the ancillary services to the market, so you get paid for that. And then it needs to follow through on that, right? Because if during the time you've offered those ancillary services, you're called by the grid, you need to be able to deliver them. So it's very important that your forecast here be very accurate, and that you plan the usage of your battery within the constraints of the battery itself, right? There's cycling constraints, there's state of charge, depth of charge constraints that limit really how much you can use that battery. So all of that needs to be put into the plan. And so this is another very different example, though, of how we can use an energy management solution in a real use case to achieve an objective that's really focused on the electricity sales. That's all that I have for today. So thank you very much for attending. I hope that that helped make it a little bit more clear what an energy management solution is, how we define it, and some ways that we can put it into practical use. Do we have questions? A few more minutes, I think, available. Yes, sir.
U.S. market, comment on the U.S. market. Yeah, so obstacles to deploying, adoption rates amongst the key decision makers in power generation in the United States.
Yeah, okay, yeah, very good question. So how do you deploy this? So what are the obstacles in introducing a system like this to power plants within the United States? In the United States, obviously, there is a major concern around cybersecurity protections. You have to have the appropriate plan in place for redundancies of the critical power plants being considered critical infrastructure, right? So it's very important that you follow certain standards in how you construct a system like this that can fulfill like NERC-CIP obligations around how you do information management, how you construct the architecture of your systems on-premise, or is it running in the cloud? Even how was the product developed, right? Like, did you create the right type of risk assessments? Did you create mitigation plans? Did you properly vet the vendors that supply into this, right? Did you test your system? Do you have these results to be able to share, right? It's a pretty big lift, I think, to be able to provide all of that information so that you can get over the regulatory hurdles. So that's one obstacle. I think another key obstacle is always you're heavily reliant on data, right? And data gets messy, right? I don't want to make it sound like that's a trivial effort to build those models. I think a lot of times you would see, like we have data scientists who are certainly experts in how you build these types of models, and they need to spend time working with customers to understand the data in great detail to the point where you can kind of account for any kind of unexpected operating scenario. Like what are some of the outlier scenarios? You don't want your system to give you a bad plan and then you lose money because it just wasn't aware or wasn't able to consider something that it didn't see intrinsic in the historical data. And so this is, I think, a part where data scientists team really need to work and test the solution with our customers to make sure that all of these unexpected scenarios are accounted for, or at least is there an appropriate plan in place if there's a time when the system is not able to consider some type of an outlier scenario. So I think like that is not a trivial effort, so that too is another type of obstacle. Any more, or we'll wrap it up? I don't have any jokes, unfortunately. I didn't think of it. I have some bad ones as a father, but I won't subject you to that.
I'll bring you the mic.
We can also have the audience tell jokes, I think is fine. Yeah, okay, thank you very much, everybody, for your time.